Arnav, is this function clear to you in inverting in a circle?
Kind of, but not totally.
Not completely. Okay, right. So we'll prove some properties of it, and then it will be more and more clear. Right. So at the moment, as we said, that we are considering these functions gamma c on E star, E star, and these functions are obviously taking E star to E star, and these are bijections. You can check that this is a bijection, but it's because you have this property. From here itself, you can show that it's a bijection. And what are the properties we have noted? We have noted that gamma c restricted to C is equal to identity, just like reflection restricted to the line is identity. This right identity. Okay. But as I said, we should ask what does it do to interesting subsets of the star. So this way we will also understand the function better and better, because usually it is not introduced as a function. If you're in high school, then it's introduced as some sort of as taking a point to another point. It's a function. But let's make this claim, and then we can understand the function. Is that you take gamma c of a line. I mean, obviously, this is a bad notation. I mean, I should this means that because gamma c takes points in E star, not lines in E star, right? But line is like a set of points, and so in that sense, I'm saying the image of the set. Okay? So this is fine. Is this notation okay?
Okay.
All right. Yeah. I mean, that's what we do, right? So when you have a function f from a set A to set B, we have a set C, but then we also speak of FC, where we mean it's the image of the subset. Because really, I mean, yeah, think about it. So what do you think this should be? That is the question. So let's draw a picture. And so maybe we'll take the function as at the origin. Okay? And draw some pictures. Maybe I should draw this proper circle, but anyway, dotted circle. Now, what do you think happens to the line? What line? That's the question. Right? So if I take this line, can you tell me what happens to this under this function? Obviously, this line comes inside the circle, right? Correct? This line will come inside the circle. And what will that be? That will actually become a circle. It's not difficult to prove that it will become a circle. So roughly, so what kind of circle will that be? That circle will pass through the origin. Okay? I'm saying all this, but you have to prove all these things. Because this is a high school geometry. I'm not visit to prove this. It's proved in that book because it's a book. So maybe they prove everything. It's that kind of book. So probably proved in the book, but I am not proving it. Okay? It will be a circle which will pass through the origin. You can use those definitions. Or you can also, if you like, you can see inversive geometry. There is a more geometrical treatment with a nice this thing by Coxeter. So Coxeter, of course, HSM Coxeter, great geometer, classic geometer kind of. HSM Coxeter, he has a book, Geometry Revisited, and there I suppose there is a chapter on inversive geometry. Geometry Revisited, not his first book, where he does introduction to geometry. I suppose that won't have this, but Geometry Revisited will have. He also has a book on projective geometry, but I don't think he has a book on inversive geometry. It's in this book itself. Well, these are the things that will give you the intuition, right? To do. Otherwise, you see some people moving so fast in mathematics, some people not being able to. Why? Because being able to see these things, if you don't do it from the basic books, and try it, try to prove it. So I mean, it's clear that it will pass through the origin. Why? Why? Because I mean, you can think, right? I mean, if you go farther and farther down to farther and farther to infinity, then the image of these points will be closer and closer to the circle, right? And so this will be there. If you include that infinity point on this line, that will come down to this circle. And why will it be a circle and not a parallel, something ellipse? That you, yeah, when one wants to sit and prove all those things, I'm not going to do it. So this will actually become a circle, yeah, through the origin. Also, if you just Google inversive geometry in Olympiad, you will get several Olympiad handouts. And choose your favorite one. Fine. Actually, these are the things which you can actually discuss with high school students also, and they enjoy it. It's basically something that sort of goes in the verbier. I mean, what do you say? Colloquially, we say that it converts lines to circles to lines. So a lot of Olympiad questions where they will have like complicated geometry problem, right? They'll have lots of let's say concentric circles, so on. Then one can invert them about some suitable circle, but then they'll become parallel lines. And the problem changes, but maybe what you want to prove doesn't change, and so you prove it there. And it's a very interesting business. But we don't have the time to get into that unless we do a separate class on geometric treatment. But this thing. And then let me ask you one more thing. What happens if this line was like this? Then what happens? Then what circle are you going to get? Let's say it's given that you will get a circle. That's a fact. What circle are you going to get? By applying gamma c. So I'll just give you a small example of a point. This point, where will this go? You have to send it somewhere here, right? But then what will be the circle that you will get? Right? Well, you know, because the circle is determined by 3 points. I'm asking this question because that's the theme of the discussion. Because this point is fixed, this point is fixed, you know that, right? And you know that 0 will come into play. 0 will be the image of the point at infinity. So it will be the circle that passes through these 3 points, and you know there is a unique such circle. So it will be a circle which is coaxial with coaxial, not the wrong word here, sorry. It will be a circle like this. Yeah, not like this, of course, but you understand. Yeah. So you can come, because that's a circle. A circle is not a random circular object. It's a circle. So it's determined by 3 points. If you know 3 points on a circle, you know the circle. Right? So a lot of interesting things can be said. Yeah? And these things you have to sit and prove. So this is good. And remember that tangent definition I gave, that's equivalent to this definition. You can use that definition also. Okay? Or you can also read this from handouts. But then finally, now I want to do further, they call it abuse of notation. I like, don't like to say that. But it's a further, extending using the same notation. You see, first of all, the function takes points. Now I'm taking subsets of the domain. That's what I was doing, subsets of the domain, lines and circles. And obviously, I mean, if this line goes to this circle, then this circle will go back to this line. Why? Because of this, right? This is a very interesting math. Okay, for every circle we are getting a function. Remember, but if you fix a circle, it's a very interesting function. And yes, it is already you can see so interesting. Flips the circle and all. So I was looking at that, but now I will just conclude all this by saying that it takes inversive lines. I mean, rather just summarize all this by just saying that it takes inversive lines to inversive lines. By this I inverse inversive. Correct. I mean, of course, here I am saying like a set of sets. Yeah, but you understand what this means. So, is it clear from
Can
the
you just
definition?
repeat the last one?
Yeah, the last one is just a combination, right? Inversive lines means what? It means lines and circles, right? I've already said that lines go to circles, or lines can go to lines go to circles, or lines, and circles go to lines or circles. So that's what I've written. Inversive lines means lines or circles. Correct. So that's why I'm saying that it's a collection of lines and or circles, and they will go to, because see why we are saying like this, because lines don't go to lines. Lines can go to circles, or they can also go to lines. If you're reflecting, then a line goes to line. If you're reflecting about a line goes to a line. If you're reflecting about a circle, a line goes to a circle. So it depends on the C, it depends on which line it is, and blah, blah, blah. So it cannot say, right? But you don't know that if you take lines and circles, then that collection will be in that collection after taking the inversion. Okay? That is the interesting thing. You enlarge your sense of the thing, then you see that if you just talk about lines, then you say, oh God, this is a bad motion. It takes lines, it doesn't take lines to lines. I'm not going to consider it. But then wait, it takes lines to circles. Ah, nice. So we'll consider lines and circles, and then it's a good motion because it preserves that class of objects. Okay. All right. So this is a basic, I just did sort of, this is a high school review of high school thing. But now we want to move into something more, which actually you will find easier because you are doing the college maths now. So you and maybe those topics you didn't do in high school, but that is not a point at all. Yeah. By the way, I think I did not say this. Maybe should I say this? So if you are considering the unit circle, then the inversion, then complex number z, a point I'm representing by a complex number z, it goes to a complicated point if you write it in the Cartesian coordinates. But if you write it in complex coordinates, it goes to very simple. You can prove that this is same as that. No doubt. I mean, you can write all the formulas in coordinate geometry and prove that all of them. So, I mean, yeah, maybe I should given you this definition to make life easy. But then maybe you won't see why line goes to circle, or you can see from this. This is another thing, but this only applies to when you apply the unit circle. But when you take a random circle, then what happens? That's what we should discuss. So the point here is that the point here is this, that you have a function, right? So you have this family of functions where C is an inversive line. Right? You have a family of functions indexed by a family of collection of geometric objects. For every circle, you have a function. For every line, you have a function. For every inversive line, to say in short, you have a function. For every inversive line, you have a function. Okay? But there is a particular there is a particular function which has a really simple representation in complex numbers. Now complex numbers come to PSL to C. So complex, one particular circle के लिए the formula is very, very simple. For one particular circle, the formula is very, very simple. What is the formula for other circles? That is what one can wonder. The formula is not, that is the claim. And so the for that theorem goes as follows. So this is the theorem. So we are saying maybe I can first explain it in the picture. So suppose you have the unit circle, your good circle, unit circle. Now things are becoming a little easier. First they were not easy. You have the unit circle, and you have this, and then you have some other random circle about which you can do inversion, but maybe you won't like to. It's better to do here, right? So how do you connect? So how do you connect gamma C and gamma? I don't want to call it 0. You can call it 0. Gamma naught is better than gamma 0 in this case. Gamma. We want to connect these two functions. So what do? If I take a point P in the plane, I want to understand its image under this circle. Okay, I want to understand its image under this circle. Right. How do I do that? By understanding its image under the original circle, under gamma 0. So I want to understand gamma CP, okay, by looking at gamma 0. So you take another function alpha. They are using alpha in the book. This is going to be very related to the change of basis in linear algebra, but here the basis change is not linear. You will see conjugate matrices, change of basis, that kind. Not linear. What you do is you take a function from E star to E star, okay, such that, and you can take the function from our collection gamma C. From this collection, such a function will be available. You can prove. So what this function will do is it will take this gamma C somehow to gamma 0. Nothing more we are asking. Just image of gamma C should go. This circle should go to, circles goes to circles, right? Circles can go to lines also if you pick a bad circle, but some circles will go to circles, right? If you take the circle outside and invert about this circle will come inside. Yeah, I hope that is correct. You will agree, right? Circle will go to circle. Outside circle will come inside somewhat. Yeah. So that's the thing. So basically, we want some other circle which will send this circle to this circle. It's possible. I mean, you have to possibly take a circle which contains this circle. It's possible, right? You have to use your imagination, but it can be done. You can use formulas. This formula is there. You can use this formula. Take this 3 points. Something. Take this. Can be done. So, not getting into that. We'll prove that this is some. Yeah.
These things are relatable with the group actions.
Yes, because I mean this is sort of the background. I mean, so what is happening is what is happening is that this collection gamma C is a group. Right? And this group is now acting on this plane. Okay. And then we will take a subgroup of this, which will be generated by, I will tell you, two product of two things. Okay. And that subgroup we will show is isomorphic with this subgroup PSL2C. And then we will prove that this subgroup is simple by looking at this subgroup instead and looking at its group action. We will be able to prove it. There are other ways to prove the simplicity, but it's, I mean, because if you want to prove a PSLN, then this method does not work. Then either you have to do n-dimensional geometry, and it becomes actually, that becomes, I can do it, but that becomes slightly complicated. That I'm not getting. In that case, if you do PSL and C is simple, then you will need more group theory, some other correspondence theorem, which is easy, but and then you will need something. Not say everything. Yeah, that's complicated. You can even this is true for non-commutative division. Actually, if you think about it, these things are very simple. And the point is that, look, how much group theory can you do without knowing any other geometry? Not much. Because what is there? What do you have? You just have some symbols and some rules of manipulation. So if you don't interpret your groups as some interesting geometric objects or something, what can you do with the groups? Or if you don't want to interpret it geometrically, then you interpret it by some other ways. So there are many other ways, but I'm not getting into it. I don't basically know all. I don't know maybe 1% also. There are too many. But geometry is one of the ways to approach this. Anyways, so right, but yeah, so I understand. Yeah, we are going taking a little longer. That is because you have not seen this. That's why. If you would have seen this, then I would have gone directly to this. I would have started with this group of inversions of the plane. But so let's continue. Let's continue. I mean, we can go a little longer today. It's not a problem. Yeah. Let me know when you want me to stop. Any one of you is tiring then. So, anyways, I'll just move quickly. Then. Okay. So the point is that there is a circle, but so is it clear to both of you that there is a circle which takes this circle to this circle, right? Right. So that circle you take. Okay. This will be actually important. This is called transitivity of the group action. Okay. This is called it's transitivity in a stronger sense, triply transitive. We will see it. So this thing is this thing, and now what? So alpha. Okay, so let me see. So alpha takes this circle to this circle. Yes, and our goal was to take the point P and connect it with. Right. So what should I do? If I look at, because see, eventually, I don't want to look at the theorem. I want to just do it on my own first, at least. And then I want this. Pakka. You want this. This is the thing you want. So if I take alpha inverse P, right? This alpha inverse is again an inverse. It's the same actually. It's alpha only. Alpha is an inversion. And then I consider the inversion about the origin. Okay. And then I apply alpha again. Alpha inverse will give me the coordinates of name. Yeah, maybe actually it doesn't matter, but still, hence I write like this. Yeah. So this is my claim. Okay, this is my claim. All right, that that this function which we are getting by conjugating our function gamma naught, this becomes this function. Okay, let us see. Let us see. How do you prove it? How will we prove it? Let's see. So what you do, you will use the clues. You'll use the clues, right? Yeah. Is it clear, Arnav and Vaishnavi? Is it clear, both of you, what this function is? This is again a function. It's an element in the group generated by these functions, right? Because these are like just composition, right? Composition of functions. So this is a function from E star to E star. Is that okay? Hello?
Yes.
But previously we have taken the function instead was gamma c, right?
Uh-huh.
And how we are again considering it alpha?
No, alpha is another function. No? We cannot take another function.
Okay, and then what is
And then we're taking composition of functions.
okay.
Correct? Yeah. I understand. But this is also, it will also be an inversion. This will also be one of these functions. And my claim is that it will be actually gamma c. Okay? And the philosophy in this lies, as you know, in group theory, that the elements A and G inverse AG are same in all respects. I mean, they have all similar properties, right? That's why it is similar to that. But let's see. I mean, this is all back and forth intuition, right? I mean, using group theory intuition, geometry intuition. जैसे भी करके, you want to know what is the truth. Proving is not difficult. Yeah, maybe. But let's see, I want to show this is C. So कैसे करेंगे? We will try to first show that this thing on, I'll take a point X in C, and we'll see where it goes. Tell me where it goes under this function. You see, it's not magic. Alpha X is on the unit circle by definition. By this, right? Alpha X जो है, that goes on the unit circle if you apply alpha X, right? And then alpha X, now if you apply gamma naught, it doesn't do anything to it by definition. That you know, because you're inverting about gamma naught, and alpha X is here. Maybe I'm writing wrong. Right, this, and alpha takes it to alpha X is here. So this and this is just X. Boom, X is okay. Okay. So you see, this function fixes points on the circle, points on this circle, on this circle. Correct? Right?
Just draw the pictures clearly.
Yes.
From the start.
So yeah, right. So the picture is what? I mean, if you take X on gamma, on this capital gamma, and apply alpha X, then you know that it goes here somewhere, right? On gamma naught, because it goes to oh, I see. Yeah, so that's what I wrote wrong here, right? I'm sorry. Yeah, this is unit circle. That's what I had in mind. I wrote it. Yeah. So this X goes to the unit circle, and now you apply gamma naught. So it will remain fixed. That's what I discussed earlier. And then you apply alpha inverse, so it will just send it back. Exposed. This is not a proper picture. Proper picture will show you the entire geometry, how it goes. But if I do that, then I have to do it in a separate class. I don't want to, because that becomes a geometric details which are not important. Those details. Okay, fine.
What gamma naught is doing here?
Gamma naught is so gamma naught you interpret from here. Gamma naught is an inversion about the unit circle, right? So gamma naught is gamma unit circle. So it will fix the unit circle, right?
We have at unit circles, and why we need to fix it unit circle?
No. Gamma naught is a function from E star to E star, and it fixes the unit circle, meaning that the image of the unit circle will be the unit circle. Every point will be on that point. Right. So what I'm saying is this gamma naught. This is a function from E star to E star, right? Correct or not? And if you take a point P on the unit circle, then it goes to P if P is on the unit circle. Why we need to fix it, I don't know, but it fixes it. That is clear, right? Because it is inversion about that circle. That's the definition of gamma naught. By definition of gamma naught, it fixes the unit circle. Fixes points on the unit circle, point points. Okay, right? Gamma naught, you remember how it was defined, right? Take a point P, then you join it with the center, that is the origin, and you invert it. That function. So that function, if you apply to points on the circle, it will not move it. And that is the function gamma naught. Gamma C is a different function, right? Gamma C just doing that 2 points on the other circle. And alpha is another such function, which is sort of the intermediate. Right? So we have proved basically that this thing restricted to gamma actually is equal to identity. It doesn't do anything. Okay? This is half the proof, because that is what gamma C also do. Now you have to just show that this is also an inversion about something. You have to show that this is also inversion about some circle. Okay? And it is not difficult to show. You can show that is also an inversion. That proof is written in the book. I'm not getting into that. Just, yeah, it can be said. I'm not getting into that. But I have proved the main thing. So this is the situation. All right. Vaishnavi, is this clear so far? The picture, what we are trying to do.
Yeah, like little bit like some. I have to see it.
Yes,
First
certainly.
sentence.
Yes, certainly. Yeah, this is sort of giving you the landscape. Now, when you read the chapter, you will see that it will be very, very. Okay. All right. So now comes the group. So we have done all that to set that was the background. It's sort of the background this thing. Now we will go into the inversive group. Yeah, 4 minutes are left, but we will again take a break. It's or maybe let me define inversive group after the break. Maybe I can. Yeah, how about we prove that lemma, right? Where we said, because maybe that can make you more comfortable from it. So you take this and you take this line, and if you are doing inversion about this line, I mean inversion about this circle, then why does it become a circle? Right? Let's try to prove. Okay. And let's consider this is origin, and so what we are applying on the plane is gamma naught, and then this will become a circle. Okay. So obviously, gamma, we want to show that gamma naught of L. So please help me to prove this is a circle. How to do this? Any ideas? So let's take some points. So if I take a point P, where does it go? It goes inside. Yeah, I also don't remember these proofs. But it's not to remember, it's to do. And right, you will get some point here, P prime, and this point is P prime, right? Yeah, there has to be some simple way. So the set of points that you get, that form the circle. For example, this will go to some point here, right? And similarly, so you have to show that this thing is a cyclic quadrilateral because origin will also come, right? Yeah, so origin is fixed, right? And these proofs are easy actually. If you just or if you use the formula which we wrote 1 by z bar, then it comes obviously. But synthetic proof, yeah. So the infinity goes to origin. I have to show that this is cyclic. Yeah. How do we prove this? Synthetic proof. Yeah. Okay, let me think. You guys also think, and then we'll again meet after the break, and maybe half an hour more we can do it for that.
On Zoom or Google Meet?
Let's continue on Zoom only because I think it's good to take a break. These discussions are. I also need a little break. Okay, it's going to end, so I'll think about it on paper. Join after 10 minutes. I think it's less than 10 minutes. Join.